Welcome students to another video lecture with Mr. Connect. So what we have done in this lesson is we're going to try and combine 3 lessons together that all focus around one topic, which is probability. So these will align with the textbook in 10.6, 10.7, and 10.8. And what we'll be covering in this lesson today is how to find the probability of a simple event, how to find the difference between a theoretical and experimental probability, and then lastly, how to work on finding the probability of a compound event. And everything should grow upon each other. So go ahead and pause here and copy down what you see. Okay, welcome back. So our essential question is focused on how to find the simple event, how to compare and contrast theoretical and experimental probabilities of real-world problems, and also how to derive or solve for the compound probability of events occurring. So our first slide here on the right is ways to describe probability. So really, we have 4 different ways you can describe probability. We could use words, such as impossible, unlikely, as likely as not, likely, and certain. In science, we will actually start to learn that most things are not impossible and most things are not certain. They're going to fall in the realm in the middle. So words are really not the most precise way to explain something. It can sometimes give us a ballpark of where something is. The next way we could use to explain probability is through fractions. And just once we mention fractions, your brain should start going, oh, well, we could probably use decimals. And you can also use, lastly, percents. So we're going to have 4 separate ways to explain the same exact probability. We're going to either ask to be used words, fractions, percents, or decimals. And all 4 of these are viable. Again, the words is kind of the weakest possibility because it doesn't always help us exactly know, while fraction, percent, or decimal would give us an exact number that would correlate with the probability. So moving on, I'm going to jump 2 slides ahead to have you copy down what you see. Please leave spaces wherever you see spaces. It's going to be really important in this lesson that you pay attention to me when I ask you to leave space, especially in the middle part of this lesson, where a lot of it's going to be done in class when we run an experiment. So again, go ahead and pause here and copy down what you see. All right, welcome back. So the first thing we're jumping into is simple probability. And this formula here, it's something you're going to want to memorize. And it's really much simpler than the words that we use to explain it. So first thing, the way you say this funny looking P parenthesis outcome parenthesis is expressed right here. We say that way of writing it, the probability of the outcome. So the P in that expression stands for probability, and we're talking about the outcome. So to use this as a verbal explanation, this P of event would be probability of the event plus the probability of the complement equals 1. So we're going to learn that to find any probability, all we're going to need to do is put that chance of the specific outcome on the top, and we sometimes call this specific outcome the event. And then on the bottom of the fraction, you're going to put all possible total outcomes. So it's that total possible outcomes on the bottom. A really simple example here would be flipping something heads or tails. When we have a coin flipped, we either will have heads form or tails form. So there are 2 total possibilities when you flip a coin. And you're either going to have the event of a heads forming or the event of the tails forming. So the probability of heads being flipped on any coin is 1 over 2. So just a really simple example of how to do that. The complement to heads being flipped, a complement is something goes along with something else, is also 1/2 because the probability of tails being flipped is 1/2. It's important for us to learn this little formula down here. Anytime you combine the probability of an event happening and its complement happening, it will always equal the number 1. Remember from our previous slide that when we have this number 1, that's the same as saying certain or 100% of everything's been calculated. So the probability of an event plus its complement is always equal to the number 1. And their problems can either focus on asking for the possibility of an event or its complement. And that allows us to solve problems multiple ways. Just always pay attention to the words. So in our first example, we have a bag that contains 7 pinks, 2 white, and 6 blue marbles. What is the total possible number of marbles in there? Yeah, you're right if you said there's 15. Now, 1 marble is selected without looking. That means this is a simple event. We're just going to stick our hand into this bag, and we're trying to figure out what's the probability that we pull out a blue marble out of that bag. So the probability of a blue marble is equal to the number of blue marbles on the top. So how many blue marbles are in our bag? Yeah, you're right, there's 6. And we divide by the total number of possible outcomes, which means that's 15 in this scenario because we have 15 total marbles in our bag. And the last step of any fraction problem is to simplify it. So please never leave your fraction unsimplified. So the probability of pulling out a blue marble out of this bag in this example is 2/5. That's the same as saying 40% chance that we pull out a blue marble. We're supposed to use words to answer this, so go back to that chart on the first page, and what is the probability of a blue marble showing up in words? Is it going to be impossible, likely, unlikely, as likely as not, or certain? You are correct. Since we are below 50%, but we're bigger than 0, it is unlikely that a blue marble is pulled. Kind of makes sense. So you're going to see all we're really doing here mathematically and skill-wise is creating a fraction and simplifying it. Sometimes we may have to do a little bit of subtraction of fractions, but I don't believe any of this math is overwhelming. It's learning what the vocabulary is asking for. So moving on, we have example 2. And in this example, we're going to find the complement. So what is the chances that we pull something that's not blue? So the probability of not blue happening. And strangely, I wrote in blue. Okay, so with the probability of not blue, how many marbles in the bag were not blue? Yeah, you're right, there's 9. How many marbles are in total? There's still 15. Once we simplify the not blue fraction, it comes out to be 3/5, or 60%, or it is likely we pull out a not blue. That's just one way. The other way I could have figured the same problem out is I could have used the probability of blue plus this unknown probability that I didn't know, and it all had to equal 1. So minus 2/5 from both sides, and you would have came up with the same answer. The probability is equal to 3/5. So remember, when you're finding a complement, there's more than one way to do it. You can either find the probability of the not happening, or you could just subtract from 1 based on the previous part of the problem. Well, that's how we find simple probability. So now we're going to move on to actually how we use simple probability a little bit more. And it's going to be important in the next few slides. You leave space when I ask for it. Because for the most part, we're going to explain this middle part of our lesson in class together when we run the dice experiment. So moving forward, please make sure to draw the squiggly line I have up here. And make sure, because we're moving on to the 10.7 part of our lesson, where we're going to learn about theoretical and experimental probability. So again, go ahead and pause here and copy down what you see. Awesome. Welcome back. So Theoretical and experimental is pretty simple. Theoretical is what you were going to do before the experiment. So it's imagining as if this experiment was run in a perfect world. Okay? So imagine if you're rolling a 6-numbered dice in a perfect world, what is the chances that the number 1 shows up? So the probability of rolling a 1 on a die is there's one number 1, and there are 6 possible outcomes on any 6-numbered die. So the chances of rolling a 1 is 1/6. What's the chances of rolling a 2? Yeah, you're right. It's also 1/6. You may have started to recognize a pattern at this point. What's the chances of rolling a 3? Yeah, it's also 1/6, and 1/6, and 1/6, and 1/6 for the others. So theoretically, when we roll a dice in any experimental process, we should come up with 1/6 of the time 1 show up, 1/6 of the time 2 show up, and so forth. We're going to learn in class that when we run this experiment, we sometimes may end up with different results than we expected. And we're actually going to run this experiment on, not period 5, we're going to run it on 4/3/18 or 4/4/18 this week. So, theoretical is before an experiment. We can calculate theoretical probability without running an experiment if it happened in a perfect world. Experimental probability cannot be run until after you create the experiment. So in class, we're going to roll a die a bunch of times together and find out if we end up with 1/6 of the rolls being 1s, 1/6 of the rolls being 2s, and so forth. What's your hypothesis? Do you believe that the experimental probability is going to equal the theoretical probability? Or do you think there's going to be some difference between the two? Yeah, we'll figure that out in class if you were waiting for me to give you your answer. So we're going to move forward here, and these examples I'm going to have you copy down, but we're not going to be able to answer them until after we run the experiment. So go ahead and copy example 3, part 1 and 2 down, leave space, and we'll actually answer this part of the problem in class after our experiment. Welcome back. We're moving on to the last part of probabilities lesson, compound probability. And what the fundamental counting principle is going to state right here is anytime you have 2 events that are directly connected to each other, what you need to do to find the probability of both occurring is multiplying each simple probability together. So a lot of words here, but it's quite simple. What we do is we take each simple probability and multiply them together. Please, I'm going to jump 2 slides ahead, pause here, and copy down what you see. Welcome back. So we're about to go over example 4 here. And the key for this compound probability is reading the directions and making sure you understand all the outcomes in which events we're actually talking about. So in this problem, Bailey's family is creating a furniture set. And in this furniture set, we have a bed, a desk, and a dresser. Well, that's 3 different categories that we have. And in these categories, there are 2 beds, 2 desks, and 2 dressers every time. And we have, in these categories, 2 beds, 2 desks, and 2 dressers. So we have beds, and there are 2 of them that we can actually choose from. We have a desk, and in the desk category, there are also 2 things we can choose from. And then we have a dresser. And in the dresser category, there are also 2 types of dressers we can determine or choose from. So right now, we're trying to find out how many different furniture sets could they select. This is another way of asking total possible outcomes. And this is common in compound probability problems. They really just want to know how many possible combinations or outcomes are created. Well, to figure out our answer, all we have to do with these 3 numbers is multiply them together. And 2 times 2 times 2 is the number 8. So there are 8 possible furniture set combinations. We're going to see a couple more examples that I'm going to actually solve through in class, but I wanted to get the basic probability problem or compound probability problem shown. So I'm going to jump a couple slides ahead, and you're going to have example 5 and the process for how we actually start using tree diagrams to answer these. So please pause here and copy down what you see. Nice, welcome back. So we're going to actually evaluate example 5 in class together. But it's no different than the previous furniture problem, dresser problem we just went over. What we'll have to do is take each of these possible simple events, find out how many outcomes each have, and multiply all the outcomes together to find out the total number of license plate combinations possible. So moving on to building our tree diagram. The key to drawing a tree diagram is really leaving enough space for it. We can draw tree diagrams that look like vertical, like this, that go from top to bottom, or we can actually build tree diagrams that are from left to right and grow as we move from the left to right side. Again, it's very similar how you draw it. The key on any of these, though, is to leave enough space for the branches further down on the tree. So in this problem, we have 2 events. We have this first event, the box of cards being pulled, and then we have the second event, a heads or a tail. So we know they're connected because of this sentence. She will randomly pick a card from the box and record the number chosen. So they're trying to connect these 2 outcomes together. The key for this is to separate the 2 outcomes. The first thing we are doing is we are choosing a card from the box. And anytime we choose a card from the box, that card is either going to have the number 1, the number 2, 3, or 4. Now we have to assume after we choose the number of box or card from the box, our second event is flipping a coin. So this first branch of our outcomes is assuming that we chose the card number 1, and now we can either have a heads in the number 1 form, or we could have a tails in the number 1 form. So that means we either could have flipped the coin heads and chose a card 1, or we could have flipped the heads or coin tails and had the card number 1 shown. We also could have the outcome where we had the 2 card pulled. I should keep my format correct. I apologize that I changed that. We should show that we have a heads being thrown in the number 2, or a tails being thrown in a number 2. Notice I'm using abbreviations for our possible outcomes to make sure it writes faster. Tails 3, we also have heads 4, or tails 4. It is this last part of our tree that shows all the outcomes. And let's just make sure we have enough outcomes listed there. If we had 4 possible cards and the heads versus tails, which is 2 options, we should have 8 outcomes on the final line of our tree. Turns out we have 8 outcomes on the final line of our tree, and we know exactly what those outcomes would be. So that's where a tree diagram helps, is it doesn't just tell you how many possible outcomes there are, it allows you to start creating every possible outcome as well. We'll go over this further in class. Can you please make sure to leave some space after the tree diagram I just drew, and then go ahead and write example 7 down. That's all for today's video lecture on probability. I apologize it's a little longer than the rest. We did combine 3 lessons together that all focus on probability, so I felt like they should all be on the same note. If you have any questions, as always, please write them in the question column and ask them in class. It's good to be inquisitive and ask questions. That's how we get help. I'll see you all soon.